My name is Franco Casillas, and in this presentation, I will talk about YVCO superconductors. First of all, what are superconductors? Superconductors are materials that exhibit no resistance to electrical currents when they are cooled down below a certain temperature. This temperature is called a critical temperature. A side effect that they have is the Meissner effect, which basically happens because when the electrical current imposes a magnetic field on the superconductor, it mirrors this magnetic field and generates a net zero magnetic field inside the material. On the right, you can see this effect, and there's two types of superconductors, type 1 and type 2. Type 1 superconductors will have a superconducting state with a perfect Meissner effect below this critical temperature. And you can see this illustration where inside the superconductor there is no magnetic field going through it. Type 2 superconductors have two different states below the critical temperature. One is a superconducting state and the other one is a mixed state. Basically what happens is that they have a lower limit and an upper limit magnetic field. And when the magnetic field is below the lower limit, it is in the superconducting state with a perfect Meissner effect. When it's between the lower and upper limit, the strength of the magnetic field is strong enough to quench magnetic field and make it create vortices where there's certain lines of this magnetic field going through the material. And therefore it has certain resistance to currents and an imperfect like a Meissner effect, but it's still better performance than a normal conductor state. Why are we talking about yttrium barium copper oxides? So basically, superconductors, as I talked about in the last slide, have a critical temperature, and they are usually lower than 10 Kelvin. You can see this in the right illustration, where we have before 1980s a lot of superconductors that have a critical temperature below 40, below 20, or even below 10 Kelvin. And we can see in the right that we have YVCO and other superconductors that have a much higher critical temperature. YVCO specifically has a critical temperature around 90, 92 Kelvin. And as I said, YVCO is a type 2 superconductor, and we talked about the difference between type 1 and type 2 superconductors in the previous slide. Now I'm going to talk about YVCO structure. These compounds have an orthorhombic symmetry in the crystal structure that is part of the perovskite crystal structures. Perovskite crystal structures have a nonmetallic anion that form a network of diagram connected at their vertices. This atom would be oxygen, and this octahedral will be these two trigonal pyramids that form the octahedra. They also have two metallic cations, from which one is small and occupies the center of the octahedron, which would be this yttrium atom, and the other one is a large and is located in the middle of the 8 octahedra, which would be barium. These two great ones. YVCO are compounds with a chemical formula that is shown here, and then they have or exhibit a superconducting properties when this X is between 0 and 0.65. This is because the oxygens play an important role in the superconducting state of YVCO structures, and we'll be talking about these in the next slide. Why are YVCO superconducting? So basically, the copper oxygen chains that are on top and on bottom of the structure, they attract the electrons from the octahedra in the middle. The two tetragonal pyramids contain 5 oxygens close to them, and in the sixth place, which will be the middle here, they have a missing oxygen. This causes this whole octahedron to have a hole, which would be a free carrier reservoir with a positive charge. And this makes this structure, the superconductive material superconductive. I would like to show you two animations. This left animation is the unit cell of the crystal structure of YVCO. The right one is the unit cells gathered together. Now we talked about the role of oxygen on the superconductive state of YBCO structures or compounds. But what are the role of yttrium and barium? Yttrium does not have a big effect on the critical temperature and thus doesn't have a big effect on the superconductive state of these compounds. However, barium does play an important role in this critical temperature as substituting one of the barium atoms by a different element such as lanthanum will make the critical temperature decrease rapidly because the lanthanum has extra electrons and it has a charge compensation effect, which makes the holes on the ACO structures disappear, and therefore the superconductive properties also decrease rapidly. Now, I would like to talk about the applications of superconductors. For example, superconductors can be used in medical devices such as magnetic resistance imaging instruments or MRIs. They can also be used in transportation development such as the maglev train, which is basically a train that levitates using the Meissner effect that superconductors have. And then there are many, many other um, different examples of superconductors applications, but they are really present in many, many technology devices. Now, the last thing I would like to show is the reference that I used for this presentation. And I'd like to thank you for listening.